Hello everyone and welcome to a new tutorial on UMEP, the Urban Multi-Scale Environmental Predictor available in QGIS. In this tutorial, I will teach you how to use one of the preprocessor tools, which is the meteorological data or Metprocessor, and how to prepare customize your own meteorological data to run the model. So if you access or you visit the website of UMEP, there are wonderful tutorials there available, but all the data is provided. So what I've been doing in the last 2 or 3 tutorials is just to show you how to generate your own data. So previously we generated the DEM, the digital elevation model, the DSM, which is the digital surface model, including ground and buildings, and also the canopy DSM, which is a normalized the canopy DSMs with with the relative height of trees. And we derive all these 3 layers from um, the LiDAR point clouds that and all of these were downloaded from the website, the Elvis Geoscience Australia, because this my case study is in Canberra, in Kingston. It's called the East Lakes suburb. So that's why I use Elvis Geoscience, and I generated these 3 initial input data, which are the spatial data. I also, in the subsequent tutorial, I show you how to quickly generate your land cover map or your land cover raster simply by digitizing and then overwriting the DM or one of these raster values with the rasterize tool. Okay, so now the next step is just to generate our own meteorological data. So there is one tool here, which is the name is the Metdata processor or Metprocessor meteorological processor. So here you can use any type of data, load your data from CSV, a comma separated value file, or from your own table, and you can select these variables. Um, Select the year you want and select also what type of what specific variable you want to add to the MET processor. There are some variables that are required or mandatory for most of the calculations in UMEP, and are here. They have an asterisk, and so you may need to have this data. But there is a much easier and straightforward way that I'm going to show today is using an EPW format, which EPW means Energy Plus weather file. And this, where you can find this, well, there is an EPW map. This is my favorite map to download it. Why? Because sometimes the Energy Plus website doesn't work properly. To be honest, that happened to me, not to all the users. As you can see, there is a very extensive database of weather stations. So I'm coming here to Canberra, the capital of Australia. Our site is in Kingston foreshore in this corner. So the closest meteorological stations are this one, the IWEC, and also the Canberra typical meteorological year, the Canberra International Airport Station. Okay, so you just have to click here and download from the website. This is from one building, which is the Energy Plus, and then this one is from DOE. I downloaded the data and I want to show you how it looks. I unzip the folder, and then what you get here is a set of different files. The EPW is the one that we want. We just have to right click open with Notepad, and then in the Notepad you will see a very long list of variables, numbers separated by a comma. Okay, this is a comma separated one with 8 lines of headings. Okay, um, this is how it looks, the IWEC. The typical meteorological year from the Canberra airport doesn't look very different. In fact, it's very similar, but there are a lot of data that may be missing. So it's very difficult to interpret this data, and there is a lot of information you may need for running Ladybug, Honeybee, in Rhino and Grasshopper. So that's how it looks, how they look, the two files. What we're gonna do now is just go to the UMEP, to the Metdata processor, and then we just check the data in EPW. You will see that all the rest of information has been grayed out. With that, we just click on load data. We need to choose the data sets. Let's start with the IWEC and select the EPW. So then disregard this. You just need to put here perform quality control, and then we put export data. And then what we're gonna do is put this met IWEC. That's all what you need to do, and we save it. And this value error came because there is no precipitation, no rainfall data, and rainfall is very essential for some of the models. The SOLWEIG model uses sometimes rain, and also the Suez use rain. So because of that, now is a good opportunity to load the other one, the international airport. Open, no problem, and then we export the data, and we are going to call this met um, airport. Okay, we save this, and then we don't get that error, so we have all all the most important variables. That's it. That's the whole process. Now let's explore how they look. So this is a txt for Notepad. As you see, here is the year, the day, the time, the minute, and then other relevant information for the UMEP, which are the energy balance equation variables, wind, relative humidity, temperature, air pressure, rain, downward radiation, short wave radiation, long wave radiation, and so on. Okay, diffuse and direct radiations as well. Many of the data will not use it for all the models, some of them yes. Okay, so this minus 999 means that we don't have these values for the energy balance equation um, variables. Also, the same is applicable to these data sets. Now, if you want to customize this data set, what you could do, because here you will have a lot of data to process, is you can select the months or the year that you want, and then you can replace. So for example, this could be the month number 5 or 3 or 4 or July or June, and for the first 23 days or for the first 30 days, and then you replace data. So another possibility is that you collected the data using your own devices, your own meteorological stations, and then it's just quite straightforward just to plot here all the data from your meteorological stations. This may look a bit difficult to modify. Perhaps if we open this in an Excel spreadsheet, is much easier. We can do open, we can browse. It should be here. We put all files, we use the Met airport, and automatically will detect this is the limited or fixed width. This is the limited. We are using a space and tab, and next and finish. As you will see here, very easy how is this data organizing columns and rows. So let's say that I just want to keep from run the model for the first, let's say, day of the year. Okay, this is day 1, and then you have, look, 365 days, because this is a typical meteorological year data. We just want for the 1st of January, and then between let's say 24 hours. So we're gonna just simply delete the rest. After that, we can save as, browse, and then we can rename it number 2, or only we say January 1st. Okay, and we save. Now we can go here and inspect again that our data is organized properly. Let's see how it works. This, if it doesn't work, because it's kind of the tab and a space, we will need just to modify this one here. So to save time, we can open this one and we keep from here to here, and then the same, we go till the end. I think it's easier if we start from the bottom. I have a better idea. We just need to copy the first lines. Say file. Okay. Sorry, just from here till here, and we just put edit copy, and then we just create a new text document, and we're gonna call it Met Airport Airport 1 Jan, and then we call it B. So we're gonna do this just to test which method works better. We open here and we just paste. Okay, so the other one has been derived from the Excel spreadsheet, and the second one is just like as it looks, just the raw data. Okay, finish with this, and now we can test and run our UMEP. So I already have calculated some of the, to save some time, some of the preprocessor urban geometry values, which are the scav factor. I've showed that how to do before. First, we use the DSM of the building and ground. We have vegetation, so we can use the canopy DSM. We keep these values unless you have a specific values for the transmissivity of light and for the percentage of canopy height, which is the height of the trunk. Then we select a folder. In this case, I have a folder here. Oh, where was the folder? Sorry, Meteo. Scav factor, and I select that folder and add the result, and I run it. This takes 5 to 6 minutes, so I already have that generated. Here it is the average, as you can see here. I will show it to you. The Scav factor, and this is the average Scav factor calculated. Okay, so we have that information, and now what we're going to do is, and we have the whole zip folder, we generate the other with the preprocessor, also the wall height and aspect is really easy. Again, our DSM, calculate wall aspect, and then we select the names aspect and height, and then we add the result and we run it. And this is exactly what we have here, the wall aspect and the wall height. This is how they look, the aspect and the height. Okay, we see that it's not very well defined, the some of the walls, but this may affect or not perhaps a little bit the information. So here obviously it detects like doesn't exist the wall, so that it's because our LiDAR perhaps has been very downs subsample too much, so we need to have a higher level of accuracy in the LiDAR data set, so that could be an option. That's it. That is all what we need for now. And we have the scav factor, the land covers, and we can start running the SOLWEIG for autothermal comfort. So the first parameter is the canopy, is the DSM, the scav factor folder that we have here, and the zip folder. We use the vegetation scheme by Lindberg and Grimond 2011, which is the canopy DSM. We don't have the trunk, and we keep these values. We use the land cover from our land covers, and we also derive the building grid, so we can use it to mask parts of the analysis. As I show all this in another video tutorial previously published, so don't want to spend more time on this. And sorry, it's save generated building grid, and then we use our DEM here. Otherwise, we choose this, the DEM is grayed out. Our wall aspect and our wall height. Then these are parameters that I will keep it there for just to keep it simple at this point. I already explained these parameters about the mean radiant temperatures, if it is the person standing or sitting in the previous video. Output maps that you can generate as well. And obviously emissivity of walls still can be controlled, while and albedo of walls as well, but the emissivity and albedo of ground are grayed out because you have now the land cover, so the algorithm will automatically assign the emissivity and albedo values from our land cover grid. Now we choose our meteorological data set. So let's run it with the first one to see if it works. And we estimate also diffuse and direct shortwave components for the global radiation. And then we just have to select our folder. So we can create a folder called SOLWEIG outputs, correct? We select that folder and we can add the average mean radiant temperature calculated for the entire first day or number of hours or whatever it is, the information that you have customized here. So here you have 360 days, it will calculate it 360 maps and the average for that, or if it is for a whole day, it will do the same. Okay, so let's run it. And obviously here there is a problem with the meteorological file, which is not correct. And this is what I wanted to show you. So when you derive it or you save it from the Excel, it doesn't work. That's how it looks from the Excel. So there is a problem with the space and tab, but where it's better just to use this format, which is just basically copy and paste the first rows, and then you can modify the values. Let's imagine you modify this value 67, and then you save it. Okay. So now let's replace this with the appropriate UMEP parameter. So is the the second one correct? That should be work now. So now it's running and the model is running as it should be. It takes a while because obviously the higher the resolution, the finer the grid, the more estimations that have to be performed. And obviously the longer it will take the model to generate our outputs. If you go to it is somewhere here. If you go to I think it's somewhere here, to the outputs folder is somewhere. Wow. Let me check where are the outputs. I think it's UMEP, Meteo, SOLWEIG outputs. You will see here all the information generated. So you have the building grids, which is very useful for the analysis I will show you in a moment. You have your model in a text file that it describes the surface data provided, transmissivity of live values, etc., all the settings. So you get this sort of metadata that you will use to report your simulation model. And then you have different tips of the mean radiant temperature for each and every hour that you have, or for each and every of the lines in your meteorological data. Now, that has been created. Then you have here your average mean radiant temperature. And obviously, well, this should go from 0 to 70. You can add it from there, or you can add it also from here. So this is the average. If you want to show only the values from 50 to 70 degrees, etc., you just need to SOLWEIG outputs. So there are the buildings here, as you see. You have the mean radiant temperature estimated for, let's say, midday. So at midday, you have between 22 and 35 degrees. You use the pseudo color. and you apply. So obviously we need to flip the colors. So you will see the areas that are cooler or hotter, etc. So you have the mean radiant temperature, how you use your building grids, as I showed you before, where you need to, some mistake we have done here. Yes, and it's really important. I wanted to highlight what is our mistake. These, if you notice, the values are funny because it's 33 degrees under the tree and then 24 in the open area. Doesn't make that much sense. And the error that we have done is, let's remove this. We haven't selected the appropriate. Let me remove this as well. We didn't select the appropriate processor UTC offset because this is Canberra. So you just need to check here for UTC offset Canberra. So it would tell you plus 11 hours. Okay, so we didn't did that. So we have to rerun the model. So DSM, SCABI factors, folder, the canopy. We don't need to generate this. Land covers, as usual. Where are you? Here. DEM, wall aspect, wall height. On the other side, the meteorological data, that is the correct one. The UTC plus 11. You can have this information. We can put it by default, but that's what we want. Then we add and select a folder, and then we just we can create another one called outputs to correct. Select that one, and we just run it again. Or we can save the output maps. If you choose another one, like for example the upward shortwave radiation, then you will get more maps in TIFF. Okay, we just run it. So now we just wait for the model to run. So that's the model. It's successful. We just see here the mean radiant temperature, the average calculated. Let's see if it makes sense. Pseudo color from 25, and then let's invert the color and apply. So there's something wrong here. It's 25 to 40. It was to 50. Apply. So now it makes sense. The model hotter, 41 degrees in the exposed areas like bare soil, 35.5 over the water, in the asphalt 41.8 or 42 degrees under the trees 31, in grass areas nearby the trees 37. So now the model makes sense because the UTC has been properly set up. If we do the same analyzing now another of the outputs, let's refresh this and let's check. Well, it's taking a bit. Output here. Where are you? Where are you? Outputs. No, it's not this one. Sorry. Outputs too. Let's grab the 1 p.m. and then let's analyze this between 38 and 77 degrees. So this is one day. We grab the 38 to 77. We go pseudo color, and then obviously we invert. Cooler 38, hotter 77. We apply. So you can see which walls are significantly, or which areas are warmer. So these are 76 degrees on that day. Mean radiant temperature, it's overexposed. It's a very hot day, and 41 degrees under the trees. So you have here a model that is working. Okay, you can use as I showed before, use the post processor, Analyser, and then choose the folder, which is outputs 2. And then you can, the mean radiant temperature, you can select, if you have other values, like the K values, etc. Um, short wave radiation or long wave radiation will appear here, the variable, but I think by default it's mean radiant temperature. You can show the animation as you see, 3 a.m., 4 a.m., 6, 7, 8, 9, 10, 11. So you see the mean radiant temperature varying throughout the day, correct? And then you can also estimate the diurnal average. And then is the magic here. We want to exclude the building pixels from that analysis. Why? Because it is the buildings, correct? Yeah, the buildings, because we just want to analyze anything that is not the roof. We want to analyze the autothermal comfort in the public domain or in the public realm. We can set up other daytime, we can analyze other aspects, and we just select an output folder. It can be the outputs as well. And add analysis to the map canvas and generate. So we'll generate is a mean radiant temperature map. Pseudo color again from 0. Um, Obviously, this 0 is something we don't want. So in our analysis, let me turn off this. The buildings have been masked, and we only get values for the, this is no data. That's why it's minus 999. And the rest is the value that it is useful for us. And that's how it works, the SOLWEIG. So in these last 3 video tutorials, I show you how to run your, how to generate your own UMEP input data from, or spatial data, how to generate DSMs, how to generate your own meteorological data and land covers, and now run the SOLWEIG. So I hope this will be very useful, so you can run the SOLWEIG model for any part of the world where you can find equivalent data sets. Okay, that's all for today. Stay tuned because I have new tutorials for the UMEP in preparation to run other tools. Particularly, I want to teach you how to use here in the UMEP the processor is the outdoor thermal comfort, the tree planter, and how to do also planning scenarios, different scenarios like adding trees, modifying the location of buildings or adding buildings, and testing different scenarios like changing land covers and buildings and trees, etc., and see how the mean radiant temperature changes during the day. Okay, stay tuned because these tutorials will come soon. Thank you very much. Bye bye.